So firstly, I should introduce myself. My name is Akarsh Simha. I grew up in Bangalore, in the premises of JNP and ABBA. Many science in actions, many young inventors meets. Eventually, REAP, which is a program at the Bangalore Planetarium, and used to be a regular attendee of ABBA. Made my first 8-inch telescope at ABBA with the help of Dilip Kumar. And then Prakash Subarna someday told me, go and observe all 110 Messier objects now that you've built a telescope. So that started my deep sky observing. Somewhere along the way, I met Amar Sharma, who became my observing partner for many years. There was a time when we requested Dilip Kumar to split my telescope tube into 3 parts. So we literally sawed the tube and made a setup so we could attach it. So there were 3 parts of the telescope, and we were able to transport that by bus. So many days we went to Hosahalli, which is a village near Dodbalapura. By bus, 2 to 3 of us would go and observe the night and come back. Sometimes I remember when I had finished the IIT JEE, that was the big thing, right, for 12th standard students. The moment I had finished that, it was like a relief, and there was this comet Schwarzman watchman, which was also in the sky at that time. At that point, we would go to Hosahalli every alternate day. For 2 weeks, we almost did that. So that was my start into visual observing. Then I eventually attended IIT Madras, got my BTech in engineering physics there, came to the US, got my PhD from University of Texas at Austin in physics, not in astrophysics. I'm an amateur astronomer. I should make that clear. And now I'm a software engineer in the Bay Area in California. So very, very typical to route here. You'll be surprised how many physicists are doing software. Part of the problem is, some of us realize that we don't like research. We don't like the academic culture and so on and so forth. And I was one of them. So, but amateur astronomy has continued. So I continued to almost a month after I landed in Texas, I had been corresponding with somebody on cloudy nights that had answered all my questions. So a month after I landed in Texas, I went and met this person, and he became my new observing partner and kind of mentor. So he taught me. He helped me, make my observations deeper. And eventually I ended up buying his 18-inch scope as a second hand. So that's what I observe it till today. And then somewhere along the way, I met Jimmy Lowry, who has been a big mentor for me. And then I met Steve Gottlieb, who is a very, 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 very serious visual observer. Towards the end, I will, of course, mention these names and tell you stories of their intensity in the field. And so I've been very lucky to have very good observers as mentors. So that's my backstory. And I must admit that I haven't gone observing much in the last 3 years. So I still make sure that I go once a year at least, right? But last 3 years, the transition from PhD to job and all of that have been eating into my time, and I'm looking forward to restart it. Quarantine has been very good for my astronomy pursuits. So that's what I've been doing. Okay, so that's the long self-introduction. So let me get started. This is my outline for the entire series right now. I think like I said earlier, I think it would be 3 talks. I hope it will not become 4 talks, 1 hour each. I'm hoping. There might be 15 minutes spillover for questions and discussion and so on. But if we go by the 1 minute per slide rule, it's roughly the right length. Now, this outline will change, I bet, because I'm sure that I'll keep working on it over the next 2 weeks. So today we will go, the last section we will do here is visibility of DSOs. So the way it's roughly organized is, this is theory, then we will do practice, and then finally we will do anecdotes and stories of, and share pictures of star parties, things like that. I am trying to convince, I won't say any more details, but I'm trying to convince someone to give a 15-minute talk in the last part. So maybe we will hear that also. Again, it's mostly, that last part is mostly going to be anecdotes. And that's a way where we can learn from each other's experience in some sense. So first, before we begin, I already mentioned that this is the three-part, the plan for the 3 parts. So we sent out the survey link where I had just a few questions to understand who the audience is and what their expectations are. And the survey results are about 33%, one-third split between beginners, intermediate people, and experienced in visual astronomy, right? The talk is aimed at both experienced observers and beginners. So every chapter or every topic, I start from basics, but I go very deep. At least that's how I've planned it so far. And so if you're a beginner, aim to understand about 75% of the content, and that's okay. If 25% of it doesn't make any sense to you, that's fine. You can revisit this, and it'll start making sense after a while. At the same time, for experienced observers who have already hunted Messier objects, NGC objects, so on, you will still get something out of this presentation. Maybe 30 or 40% of it will be completely boring for you, but you will still get the remaining part. So that's how it's organized. The third thing is that this talk is modular. So if you miss today's talk, you can still go to the next series. If you miss that, that's fine. You can still go to the last one. There might be some terms that are common, but it's okay. Like other than that, you won't miss much because they're very different topics. The other unfortunate thing is it's very hard to explain or share visual observing in a talk. It has to be on the field, preferably with another person, right? And so this talk will end up being very theoretical. Nothing can compensate for the experience of being in the field and learning. Hopefully this will inspire you to do that. It will give you the tools necessary. It'll clear up some of the confusions that I had when I was a beginner. And it'll hopefully give people who are already somewhere in the hobby, the tools necessary to go further. So this talk will unfortunately not teach you everything that you need to do visual observing. And that really, either you have to struggle with yourself as trial and error, or you have to learn from somebody in person. But hopefully I will try to do my best on trying to explain as much as I can through this presentation. Finally, some protocol, quick clarifications, short questions in between the talk is very good. If somebody has something I have not explained, somebody doesn't know a term and it's bothering them, they can always interrupt and ask. Let's keep the big questions and discussion to the end. Then we can have open floor for discussion for a while. So I saw some of your survey responses on what you wanted to hear about. I can meet some of your expectations, but not all. So we will not go into detail into naked eye and binocular observation. There are a lot of books on the subject. I think Turn Left at Orion is a popular book. We used to use this thing called Edmund Star Atlas and Edmund Sky Guide. Unfortunately, those are out of print. So we'll have to. I don't know what are the new books, but we can start a thread on BAS and figure out what books can explain these things. Someone mentioned about research and visual observing. Unfortunately, there's not much new research that you can do with visual observing. If you're an astrophotographer, you can actually contribute to science. That's very hard as a visual observer. So advanced observers, like my friend Jimmy, have found new objects. That's very unusual. So I would say if you want to contribute by way of doing this, aim for educating people and spreading science awareness. Aim for sharing your observations on a forum so that others can also enjoy them, and aim to do outreach and stuff like that. So I will also not go into details of how telescopes work and how to operate them. Again, this is mostly field knowledge, and if you find anyone from your local astronomy group that is knowledgeable on this topic, they'll be able to help you. Probably better than me, because I know how to operate one kind of telescope very well. But like GoTo and those systems, I have no idea how they work. Things that I will discuss that were in the survey comments. I will discuss star hopping specifically in alt-azimuth telescopes with software, because that's what I'm most familiar with. Everyone has different ways of doing star hopping, so everyone's method is just different. So I can present my method and see if that helps you. I will say some things about city observation. I would say city observation is very much like doing extremely faint objects because the sky condition makes it that challenging. So if you are a good city observer, you will really see when you go to the dark sky. It's like you have had your most advanced training. Observation techniques. I will discuss observation techniques in the next talk. I will talk about how to plan an observing tip. That's also something that someone raised. I will talk about seeing detail in deep sky objects beyond just hunting for them. So here's prerequisite knowledge that is not covered in this talk series. So I'm going to assume that you know most of this, or even if you don't know, you will still learn a lot. So I won't talk about light pollution and how it's caused. I won't talk about magnitude scale, although I will introduce it. Like if you don't know the term magnitude, I will have an introduction for it. But giving a feel for magnitude scale is beyond the scope of this talk. I won't talk about basics of telescopes and equipment. I won't talk about mounting, collimation of a telescope, operation and maintenance of telescope. These are things I won't talk about. I also won't talk about celestial coordinate systems. Now, this background is kind of assumed, but if you don't have it, I think you will still learn a lot. So we can maybe have someone explain how to use a telescope at some point, but there are books on this again. The basic stuff that I will cover are types of deep sky objects, and I will also talk about star hopping, like I mentioned. So okay, that's the beginning. Now we can start with the actual talk. So first I want to answer the question, what is visual deep sky observing? So what are deep sky objects? A deep sky object is anything that is not a solar system object and not an individual star. So things that are outside the solar system but are not individual stars are called deep sky objects. That's the term that's what the term means. Some examples are open clusters, globular clusters, nebulae, planetary nebulae, and galaxies. I'll show pictures to indicate what these things are in the future slides. Here are three examples. The one on the bottom left is a pair of galaxies. The one in the center is a nebula, and the one on the right is a really zoomed in part of the globular cluster. What is visual observing? It means viewing the object with your own eyes using an eyepiece at a telescope. So here you can see Jimmy Lowry at the eyepiece of his 48-inch telescope. That's a very huge telescope, probably one of the biggest amateur-owned telescope in the world. So visual observing as opposed to astrophotography. In astrophotography, you would attach a camera to the telescope and take a picture. Here we are observing with eyes. Now, what is the point of doing that? Not much before photography. This is how science was done. Famous visual observers are like William Herschel, John Herschel. These people found objects by their own eyes as opposed to cameras and photographic emulsions. Today, very little science is done visually. Like most science is done with cameras and particularly CCD cameras. So visual observing today is mostly for fun. It's an inspiration for young scientists, and it creates a scientific temperament. And my friend Sanat was also mentioning that it has taught him to be organized and so on and so forth. It has certainly been part of why I did a PhD. I mean, even though the PhD was in a different field, definitely astronomy motivated my interest in science, and vice versa. So I am not the only one. I know a lot of people who have been like active on BAS and ABBA and other local astronomy groups who have gone on to study science full time. So it'll inspire somebody if you share it with them. I also think it promotes conservation of the environment. The more you do this, the more you go to these far off remote places, the more you connect to nature, the more you care about light pollution and things like that. I think it promotes conservation of the environment. And finally, there is this philosophical aspect, which is like Carl Sagan's famous pale blue dot video. It is a very humbling subject. Like you're seeing light from a cluster of galaxies that lies a billion light years away. It reminds us how small we are in the universe. So that's the general purpose of it. Why do I do deep sky observing as opposed to astrophotography? This is my personal choice. Why I think it's cool to do deep sky observing. One is you get to see the real things. You get to see the real object with its real light, and sometimes that light has traveled billions of years to get to your eyes. So that's a very hair-raising experience for me. To me, astrophotography feels less personal because of this, because you're separated from the object with this camera train and computer. So I find it less personal. The other reason I do visual observing is because I think you can go much deeper for the same investment in terms of money, not in terms of time, in terms of money. So for astrophotography, you generally have to buy an OTA telescope. You need to buy a mount. You need to buy a camera, and you need to sometimes buy software. And if you put most of this in a common budget that most of us can reasonably afford, you generally get wide field images, unless you can afford these extremely expensive precise mounts like astrophysics or Losmandy and so on and so forth. It also needs hours of exposure. Whereas for observing, you combine the investment that you put in all of those and you buy one big telescope, and it'll take you much deeper. The problem is you need to know the technique on how to go deep. Plus, you need access to very good skies, and you won't see color. And in some sense, you are combining those photons to create the image in your head. So that takes some experience and practice. So that's the other reason I do visual observing. Here's an illustration. I think most of the features that you're seeing in this photograph, except for the color, of course, can be seen in a 16-inch telescope. By that, I mean the shape of Cigar Galaxy. Okay, so this is called Cigar Galaxy, and this is called Bode's Nebula. So you can see the spiral arms of Bode's Nebula in 16-inch telescope if you know how to look. You won't see this red color in the Cigar Galaxy, but you don't see those kinds of details. But you do get most of this for almost half the cost of what equipment it took to make this picture. Other reasons I like visual observing: less setup, less alignment. It feels less like going to work. I once worked in an optics lab as part of my study, and all I did there was align mirrors, and astrophotography still feels like a lot of that to me. Whereas for visual observing, you just do one collimation and forget about it. There's no polar alignment and all of that. So I feel it's less technical, less optimization is required. You don't need to cool your camera, so on and so forth. There's other kinds of optimization that you have to do, but I feel like it's overall less. But drawbacks, why you should instead do astrophotography. For visual observing, sky quality is everything. With astrophotography, you can do something in your urban environment. With visual observing, it's extremely hard. Plus, you'll probably buy a big telescope for visual observing, like 10-inch, 12-inch. These are very hard to transport. Sometimes you have to decide which car you will own based on how big your telescope is, as was the case with me. So other thing is you don't see color for most objects. You can't share your experience on social media. The only way you can share your experience with someone is to have them on the field. Unless you're a great sketcher. If you're a very good sketcher, then of course you can sketch. You can't set up your sequence and chill. You have to be running up and down, finding objects all night. And you need healthy eyes, good night vision, and physical health to do this all through the night. Okay, so that's my motivation. Some of you are beginners in this call, so here's some advice for you based on my experience. I think these are the skills and abilities you need for visual observing. You need to be good with geometry and pattern matching. And by that, I don't mean protractors and dividers like we did in school. I just mean you should be able to match and rotate a pattern in your head to match the star chart. You need to have some memory for patterns of stars because you're normally going to memorize the pattern on a finder chart and then go to your eyepiece and look at the same pattern. So you need some memory, but you don't need to have, like, if you've heard of the name George Alcock, you don't have to have George Alcock kind of memory. George Alcock actually memorized patterns of stars around the sky so he could hunt for novae and supernovae. You don't need to remember, like, that's crazy. So if you can just remember for 5 seconds what a field looked like, that's good enough. You need to know some basic mechanical and optical knowledge of how telescopes work. Not as much as astrophotographers, much less complicated stuff, but you still need to know how to use your telescope. You need good vision and good physical health. I've already mentioned this. And most importantly, you need perseverance. You need to make those efforts to go to the field, stay up all night, and find these faint fuzzy objects and log them. And that's how you get better at the hobby. So the other thing I want to say is don't expect great observations on day one. The famous telescope maker and visual observer Mel Bartel says on his website, experience is worth 2 magnitudes. So you'll see much better, like much better, if you have a lot of experience. And I think it's maybe even more. I think with time I have been and training, I think I've become much better at spotting details. And so experienced observers have also made extensive investments, both financial and time. They have invested in high quality equipment. They have invested the time and effort of going to dark sky sites. They have invested many nights, all night observing. So they have put in a lot of effort into this. And knowing and understanding what you're seeing in the eyepiece takes a lot of time. So that's why I don't expect great observations on day one, because great observations are made with experienced observers, quality equipment, and great sky conditions, all combined. Instead, how do you start if that's not what happens on day one? First of all, ask if this interests you. It's a hobby. If it doesn't interest you, then fine, there's no need to do it. But if it interests you and you are willing to put in the efforts needed to, get better at it, or you don't have to get better at it also. That's also a personal choice. But if you want to, if this interests you and you want to go deep, then that's fine. Then I would say persistence is the next key factor. I think it's if you want to eventually see very faint objects, you have to keep motivation alive by setting simple goals. So you train your eyes and vision and learn how to do this over the years, right? Instead of having a goal like I will see Einstein's cross, which is a very tough object. I'll mention Einstein's cross at the very end, in a 12-inch telescope, which is virtually impossible. Set a realistic goal like saying I will finish all Messier objects in 2 years. This is how I started. I started by saying I will finish all Messier objects in 1 year. I finished 109 out of 110 on the last day, like December 31st. So that's, I think that will keep your motivation much better than having an unreasonable goal and not achieving it. And I'd say make efforts to find and go to dark sky sites. Visual observing is very sensitive to quality of sky, so this is important. Start by learning the night sky, learning to find objects. I will talk a little bit about this. So step 1 is to find the object, and then step 2 is to practice and learn to detect the faint light and observe the object, right? So step 2 is to see the object. And I recommend observing with more experienced people. If I have become a good visual observer, it's because I had someone more experienced next to me all along. In the younger days, it was Amar Sharma, then it was John Tatarchuk, then it's people like Jimmy Lowry and Steve Gottlieb now. So observing with more experienced people will always help. And eventually you will be able to see all the detail that I mentioned in this. So don't expect to see all the detail that I mentioned in the crazy observations, maybe part 3, until you get more experience and put in the efforts needed to train your eyes and brain to do this. Okay, so that's my introduction. At this point, I want to pause and see if there are any quick questions. Is the transmission all okay?
Yeah, we can hear you very well.
Okay, cool.
There are no questions at this time, only some people struggling to see the screen still, but otherwise it's fine.
Okay, sure.
Let's continue.
Okay, now we'll get into the meat of the talk. I'm going to start by giving you a tour of what are deep sky objects and what are the types of deep sky objects, and what are catalogs of deep sky objects. So generally, I'm going to approach all of this with the angle of what do people observe, right? What kinds of deep sky objects do people observe? So here's a list of deep sky object types. You might not know what any of these mean. In a moment, I will show you pictures. So there are double stars or groups of stars. These are just groups of stars or pairs of stars. There are open clusters, globular clusters, which are kinds of star clusters. Then there are gas nebulae, clouds of gas. There are galaxies, which are like our Milky Way, big structures of stars and gas. And there are pairs and clusters of galaxies. These are the things that people normally observe. Now, this is a very high-level list of types. Each of these has their own subtypes and their own diversity. I think it's very hard to list all types of deep sky objects because there's always a peculiar one that's an exception to every rule that you've created so far. They're just very diverse. I haven't shown pictures of double stars and groups of stars that we normally call asterisms. They are just groups of stars. So let me start with star clusters. This is what star clusters look like. On the left here is what we would call an open cluster. It's a loose cluster of young stars. On the right is what we would call a globular cluster. That's a tight, dense cluster of old stars. If you're a beginner observer, you will probably love open clusters. They're wonderful to look at until you get bored of them. So I encourage you to start with open clusters. For those of you who are bored of open clusters, there's a lot of other things to observe. Believe it or not, there is a lot of diversity within these objects that I won't go into because I don't know. I'm not very deep into star clusters. Then there are nebulae. Nebulae are clouds of gas. That's as generic as we can be. Some of them emit light, some of them reflect light, some of them block light. Okay, so on the left here is what we would call a diffuse emission nebula. It's a cloud of gas that is emitting light. And it's emitting light because the gas is ionized. In chemistry, that basically means it has turned into positive and negative charges. And when they recombine, it emits light. So in the center is what's called a reflection nebula, or a diffuse reflection nebula. This is a nebula which is reflecting the light of stars. Just like a cloud in the evening after sunset would reflect the light of a star, this nebula is reflecting the light of, cloud in the evening will reflect the light of the sun. This cloud of gas is reflecting the light of some other star. On the right side here is what is called a planetary nebula. It's a shell of gas that has been thrown out by a dying star, and this shell of gas is ionized by the energy from the star, so it emits light. Just like the diffuse emission nebula on the left, this is also an emission nebula, but it's because it's so well shaped and it comes from a dying star, it has a different name. It's called planetary nebula. It has nothing to do with planets. It's called planetary because back in the day it looked circular like planets, so somebody called it planetary nebula. Now we are stuck with the name. Okay, it's just a circular nebula from a dying star. These numbers and names that you see here, M42, NGC 1999, these are all catalog designations. I will get to soon. You should know what those are. Okay. Then there are galaxies. Galaxies are probably the richest class of deep sky objects. The universe is full of galaxies. Here I've listed 3 types. There are many more subtypes, of course. Like you might have heard of barred spiral galaxies, lenticular galaxies, ring galaxies. I've just shown 3 types. On the left is spiral galaxy. It looks like a spiral, and it's probably the most recognizable thing that comes to your mind when somebody says the word galaxy. Milky Way, our galaxy, is very much like that. It's a spiral. People say it's a barred spiral, which is a spiral with a bar in the center. The central example here is an irregular galaxy. This one's called Barnard's galaxy. It just has no shape. It can be of any shape, as you can see here. On the right-hand side is what you would call an elliptical galaxy. It's elliptical in shape. In this case, it also has this jet coming out of it, of matter. Incidentally, this was the galaxy that was photographed for the black hole recently, the black hole photograph that was created, I think either this year or last year. And this jet is coming from that black hole in the center of the galaxy, or from the accretion disk of that black hole. Then there are individual galaxies, and there are pairs and groups and clusters of galaxies. Galaxies generally are part of clusters. The one on the right here is a cluster of galaxies. I know it's very hard to see on the screen, but there are tiny dots here which are stars. These are the stars from the Milky Way that just happen to be in the way. And then there are these faint fuzzy blobs which are actually galaxies that are far away. So if you search for Hercules cluster of galaxies on the internet, you can zoom into those pictures and you'll see that there are galaxies everywhere. On the left here is an interacting pair of galaxies. Now, pairs of galaxies sometimes can just come in pairs that have no physical relation to each other, but sometimes they're also like together, actually in space. And if they are close by, then one galaxy's gravitation force affects the other galaxy's gravitation forces. So they distort each other. And what's happening here is these 2 galaxies are being distorted by each other's gravitational force. We'll talk about that a little more shortly. In the center here is what we would call a compact group of galaxies. It's a group of galaxies that is tiny and close by, maybe 6 or 7 galaxies. People observe all of these. Interacting pairs are common. Some of you have already seen them. compact groups of galaxies, generally they tend to be harder. I don't know if many people in the call have seen any of these. And clusters of galaxies, of course, those tend to be hard as well. But I guess many of you have seen the Virgo cluster, which is a cluster of galaxies. So let me stop the types and get to where these are. Almost every star that you see, every open cluster that you see, most of the globular clusters you have seen, and most of the nebulae you are seeing are all part of the Milky Way. So almost everything that you see in the sky, unless you search for galaxies in a telescope or binoculars or naked eye, are pretty much in the Milky Way. The caveat is M54 is actually a globular cluster that's not in our galaxy. It's in a neighboring dwarf galaxy that orbits the Milky Way called, I think, Sagittarius dwarf spheroidal or something like that. But most of the Messier objects are in the that are not galaxies are in the Milky Way. Now there are objects outside the Milky Way. There are galaxies. Of course, all the galaxies are outside the Milky Way. There are pairs of galaxies, groups of galaxies, clusters of galaxies. These are all outside the Milky Way. But what is interesting is people also observe extragalactic objects. People observe individual stars in Andromeda Galaxy. This is really hard. I was at a star party, I think the last star party last year, and somebody was observing stars in Andromeda Galaxy. It's possible. I did not get to see it, unfortunately. Then there are, this is relatively easier. You can see stellar associations, which are like loose open clusters. Remember, open cluster is loose group of stars. This is even looser than open clusters. You can see these in many galaxies. This is not as hard. You can see globular clusters in other galaxies. That's pretty hard. You can also see nebulae in other galaxies. That's also not super hard. There's some examples that are bright enough. Most of the time when you are doing these things, you are doing those in nearby galaxies like Andromeda Galaxy, Triangulum Galaxy. These are some of our nearby galaxies where we can see these objects. Of course, if you get further than that, only Hubble can see, no, only big telescopes can see these objects in other galaxies, but amateurs can see some of them in the nearby galaxies. Okay, so that's where are deep sky objects. So I've given a rough outline of what are the types of deep sky objects, but now I'm going to show some examples that are not those examples, right? Normally, whenever we look at a list of deep sky objects, what we see is what I just showed you. But I just want to show these slides to say that there are many more types and many more details that we can look for. So here are types of, sorry, is there a question?
Akarsh, there is a question.
Yes.
The question is, what is the difference between a cluster and an irregular galaxy?
That's a very good question. More so, if the irregular galaxy is really big, then it's pretty easy to say that it's a galaxy. Especially in the case of this galaxy, it's very easy because there are also nebulae inside it. Right? Cluster normally, okay, there can be sometimes nebulae in clusters, but usually they are line of sight unless they are a globular cluster. You don't see planetary nebulae in open cluster because the stars are very young. And I don't think you ever see planetary nebulae like this in a globular cluster. They tend to be very mixed up in the cluster. So if you see, these are not actually planetary nebulae, these are H2 regions. Like diffuse nebulae. So if you see diffuse nebulae, then it's almost surely a galaxy. Now there are some galaxies which look like globular clusters, right? Irregular, more than irregular, they would be what we would call dwarf galaxies. Dwarf galaxies look very much like globular clusters. And the line between dwarf galaxy and a globular cluster is I don't know it fully, but there is some plot that you can make about, I think, the size of the galaxy and the number of stars or something like that. And that tells you where the galaxy lies in this curve, where the object lies in this curve, tells you whether it's a dwarf galaxy or a globular cluster. The line is very blurry. In fact, we don't know if Omega Centauri is I've heard that we don't know if Omega Centauri is a globular cluster or a dwarf galaxy. It's very borderline. So maybe I'll try and follow up with this because I've seen this in some paper, and they're able to tell based on some properties whether it is this category or the other. They are very, very similar. But in this case, we are able to tell that this is not a globular cluster simply because it has H2 regions. By that, I mean diffuse nebulae. Okay. Any other questions?
Akarsh, then you can continue.
Okay, sure. So further types of nebulae. So I gave you 3 classes so far: diffuse emission nebulae, diffuse reflection nebula, and planetary nebula. Now there's something called a protoplanetary nebula, which is like the reflection version of a planetary nebula. It is a stage before the planetary nebula where the dying star is not hot enough to ionize the gas. So the gas doesn't emit light, it only reflects the light of the star. So the dying star produces these lobes. Depending on how it is rotating along that axis, it can throw out these materials, and those materials reflect the light of the dying star, and that's called a protoplanetary nebula. The reason I'm mentioning that it's not ionized means that if for those of you who have done some visual observing, nebulae filters don't work on protoplanetary nebula. So if you put UHC or H beta on it, it won't work. In the center is an example of a dark nebula. This nebula blocks the light of the stars behind it. It's just like a cloud blocking sunlight, or like it's just a cloud of dark material that is blocking the light from behind it. They're usually made of molecules, and cold molecules like carbon dioxide and so on. It's ice of these molecules is what it's made of. This example here is called coal sack. Many of you probably have seen it. It's not visible from where I live now. It's next to the Southern Cross in the Milky Way, so it's visible with the naked eye. On the right is a beautiful picture of by Rogelio, whom some of you are familiar with. This is of what is called a supernova remnant. This is the result of material that has been ejected by a supernova, and that material is traveling through the interstellar medium, and it's glowing as it does this. So you see with supernova remnants, you always see these, if I may call it, tendrils of light or filaments of light. And this object called Sibais 147 is an extremely challenging visual target. It's possible to see it visually, but it's very, very hard. It takes extremely good skies and all of that. Okay, so that's a few more kinds of nebulae. I really like interacting galaxies. So here's a slide on saying some of the features of interacting galaxies. On the left is a famous pair of galaxies called the mice galaxies. What you're seeing here is something called a tidal tail. Let me draw this, highlight this region. This thing is called a tidal tail. How this is formed is, so let's say these two galaxies started out far away. Now because of their gravity, they are attracting each other. This side of the galaxy is closer to the other galaxy, so it feels more gravitational force. This side is further away from that galaxy, so it feels less gravitational force. That means this side moves faster. The one on the left here moves faster, and the one on the right here moves slower. So what happens is the material here gets dragged because it's moving slower, whereas this part is moving faster. So it leaves this tail of material. And I really like seeing tidal tails. Don't ask me why. I mean, I don't have the equipment. There are very few tidal tails that are visible in my telescope. So I usually see these from friends' telescopes, which are much better. these are called tidal tails. There are 2 or 3 of them that are very nice and visible in 16-inch, 18-inch telescopes. Here is a bridge connecting 2 galaxies. This actually is a very hard bridge. The mice, on the other hand, I can see in my telescope. This bridge is very faint. I think this is formed when 2 galaxies pass by each other and their stars get intermingled, right? So sometimes you see these bridges. Sorry, I shifted too quickly. Now, extragalactic nebulae. I mentioned that visual observers see nebulae and galaxies in other telescopes. And here are 2, in other, what am I trying to say? They see nebulae and galaxies in other, nebulae and clusters in other galaxies. And here are 2 examples. On the left is a nebula in Triangulum galaxy, which is one of our neighboring galaxies. On the right is a globular cluster that is in Andromeda galaxy, which is, as you know, our biggest nearby neighbor. So both of these are visible in amateur telescopes. The left one is particularly bright. I think you can see it in an 8-inch telescope, this NGC 604. It's a nebula in Triangulum galaxy, like I mentioned. This, I think, needs a bigger telescope. I'm not sure what is the smallest telescope you can see it in. I've seen it in my telescope. So one shouldn't be afraid of these objects. Like I mentioned, M54 is an extragalactic globular. You've already seen one if you've finished Messier list. Then there's also one called NGC 1049, which is pretty bright, which I think you can see from 10-inch, 12-inch if you're on the southern side of India. Now, other obscure stuff. These are really hard and challenging observations that very few people have made. One is seeing gravitational lensing. I put this slide to tell you that there is no dearth for types of DSOs. There are so many types. On the left is an example of a gravitational lens. This is where light bends around a foreground galaxy. Light from a background galaxy bends around a foreground galaxy and forms that ring. Seeing a ring like this is super hard. I think the best we have seen is a tiny arclet, as they call it. This object is definitely out of the scope of amateur telescopes. This thing here is called an Herbig Arrow object. What it is it's a material from protostars. That means stars that are just forming that get thrown off. These stars throw off this material, and that material hits the interstellar medium and starts glowing. So you normally see these in nebulae, other nebulae, like you see some in, I can't remember, in Orion Nebula. I think there are a few. There's some in Perseus and so on and so forth. So anyway, these are not like regular nebulae because they are formed in this special way. And I'm told that these objects show variation in a matter of weeks and months, which is very rare to see in astronomy. And so that's why I was very attracted to them. And here is a jet from a quasar. A quasar is a very active galactic nucleus. So it's the center of a galaxy that probably has a big black hole that's doing a lot of things. And those usually throw out these jets. And here is a jet. This is a very hard jet to observe. My friend Jimmy has seen it. I might have seen it in his telescope. So these are crazy obscure things. Okay, so I've now given you a flavor, hopefully, for what are the types of DSOs that exist and so on and so forth. I'll take a pause here and ask if there are any questions. I realize I'm not doing very well on time. So there's also that.
I guess there aren't any questions. So
Okay. We'll see
I
how
have
far
one
I get.
question.
Yeah,
Akash.
sure.
So you mentioned some of which we can see with 16-inch, some of which we might need, you can see in 12-inch, 8-inch, etc. Is there, are these, like, say, the Messier objects, or is there a tag which says what is possible with which kind of telescopes? or equipment?
Unfortunately, no. Unfortunately, no. But I'll get to that in the next talk. I think the best way to determine whether something. Sorry.
Nothing. Go on.
Yeah, the best way to determine. Yeah, the best way to determine if something is visible in your telescope or not is to try many different objects, and then you will get a sense from photographs. You'll be able to tell if it looks this bright on a photograph, I can see it. So you'll be able to develop that. Plus, the only other way is you look at the reports of other observers. Like I know, for example, some of these other people have already observed, so that's how I know that they are visible in these kinds of telescopes. Sometimes you just have to give it a shot and see. But that being said, almost all of Messier objects can be seen in 6-inch to 8-inch telescopes. For sure, you can see all Messier objects. The NGC catalog of objects, which I will introduce shortly, almost all of them can be seen with an 18-inch telescope. And the reason is Herschel used that kind of telescope. I think William Herschel used a large 17-inch telescope or something like that. I'm not sure of the exact details, but most NGCs you can see in a 18-inch kind of telescope.
Thank you.
Akarsh, sorry, if I might just add a quick thing to what you said. So you never know until you try, because a lot of times you hear folklore about how certain objects are not visible in a certain kind of scope, but people have actually tried and actually proved that wrong. One example being Leo 1 in an 8-inch.
Akash, there were a couple of other questions which came up.
Yeah.
So one is from Leela ma'am. Are the clusters around galaxies called as satellite galaxies?
The clusters are not, unless they meet the criterion for a dwarf galaxy, right? Clusters are clusters, but if they are, I don't know what is the criterion to differentiate between a globular cluster and a dwarf galaxy. But if it meets that criterion that it's a dwarf galaxy, then you would call it a dwarf galaxy, and then it's a satellite of the Milky Way. Yeah, there's a thin line between globular clusters and dwarf galaxies. But open clusters, generally you don't find them loose. When they might be in like tidal tails or something like that, then I forget what they're called. I guess you call the galaxy a starburst galaxy, and anyway, I mean, it's uncommon for open clusters to just be lying around loose. Whereas globular clusters can be in the extreme halo of the Milky Way, then you would say they are associated with the Milky Way. But if they are now dwarf galaxies, then you will call them satellites.
Okay. Another question is, are those black holes which are throwing out the matter in the quasar, but just at an angle from us?
I did not fully understand the question.
Okay,
so,
the question is, it is a question on quasars. So
okay.
What exactly is throwing out the matter that you said that you were able to see the filament? So.
Right. It is the so around a black hole you normally have this thing called an accretion disk where there is matter spinning into the black hole, and I don't know the exact physics of how this happens, but along the axis of rotation it throws out these materials, and depending on which way that material is oriented, they give the galaxy different names. Maybe that's what is being asked. So if the material is directly pointing to the Earth, I think then you call it a blazar or something like that. There's a special name for it. In this case, yes, it's in the case of the jets I've been showing, it's not pointing directly at Earth, it's pointing at an angle, and that's why you're seeing it go in a different direction.
Okay. One more question from Satish. Any suggestions for people with spectacles during observing DSOs? How should they watch? With glasses or without?
Without glasses is the number one way to do it, is remove the glasses so you can get to the correct position on the eyepiece. Otherwise, you will have stray light from the side hitting your eye. So you remove the glasses and then use the focuser of the telescope to adjust the focus for your eye. So that's the best way to observe. Now, if there's a public gathering and people don't know how to focus, then I usually tell people to wear their glasses while observing. so that they don't have to deal with the focus knob and all of that. But if you are observing by yourself, I recommend removing your glasses and adjusting the focus.
Okay. One more question. Can we theoretically deduce what is visible through which kind of telescope? Aperture, magnification, angular dimension, magnitude, etc.
So I think that's a very good question, and I will go into that at some point. I will mention some theory. I will get to answer the question. I will get to some theory. The problem is that the theory doesn't work well, and I'll explain why. The theory tends to assume like uniform objects and so on and so forth. There's a lot of variation that goes into it. So I would say the short answer is no. We cannot estimate what is visible in each telescope from theoretically, but you can get some rough idea. There are ways to get rough idea, and those rough ideas are usually useful.
I have a question. So if if I have only a short part of the sky I can see, say through a window just to the east, how do I know what are visible in that field of view?
You have to either know the sky well enough to know what you're looking at in that window, or you have to know the altitude azimuth of that window so that you can like go look at it in software, so you can predict what is visible in that software and so on and so forth. Or you use a go-to telescope and see if it points to the window.
Okay.
But there are these mobile apps which use the internal sensors.
That's a very good point. Yes, mobile apps. Correct. Thank you, Kirti. Kirti, right? Yeah.
Yes.
But the mobile apps are a lifesaver. Yes, very good. Thank you. The mobile apps are the way to go.
Cool. So okay, what is it? Okay, maybe later. Just a couple of names of these apps. So I presume you just point at the window and it'll tell you what can be seen.
Yeah, I recommend for Android especially. I recommend SKEYE Sky. It's developed by one of our former BAS members, or I mean, we can call him a BAS member, Harshad Joglekar. For iPhone, normally people recommend Sky Safari. I think there's a free version, and that's what I've been using for getting to polar align my platform. That's what I use. So you can use that.
Thank you.
So, okay, if there are no more questions, I will get into
Sorry,
this,
I had
fairly dry topic. Okay.
Sorry, Akash,
Yes.
one more question.
Yeah.
So let's say we are doing a manual observation, and you see something like a star, and it could be not a star, and maybe it's some other exotic object. It could be a supernova or a quasar or whatever.
Yeah.
Is there an easy way to differentiate for amateurs or not beginners but intermediates without great diffraction and all that? Is there any other easy way to understand if it's a star or something else?
If it's okay, so the categories that can be confused with star are stars, very stellar galaxies, quasars, and supernovae, right? So supernovae, because you look at a picture of the galaxy from before. If the star did not exist, chances are it's a supernova. That's number one. It could also be an asteroid, but actually, I don't know how you would tell. You hope that you put it in the Minor Planet Center's database and see if you can find an asteroid that matches that region or something like that. Visually, it's very hard to tell, right? The solution is either use a software to find out what it is, whether it's a star or whatever. Whether it's quasars will be cataloged in a database, so you can determine whether it's star, quasar, or asteroid by looking at a software. The hardest thing is sometimes you get these anonymous. Sometimes it's very hard to tell between high surface brightness galaxies, like really tiny galaxies. By tiny I mean like really far away galaxies, and stars. That there is no easy way. You just find the best resolution image that you have and see if you can tell from that. Usually there is a image service called Sloan Digital Sky Survey, and If it exists in the Sloan Digital Sky Survey, then it's easy to tell because you can look at the image and say whether it's galaxy or star. In the field, in the eyepiece, I don't think there's an easy way to tell.
All right, thank you.
Okay. Thank you for this pause. I also needed it. So I'll go ahead with catalogs of deep sky objects now. This is a somewhat dry and boring section, but I want to make sure that nobody is afraid of catalog numbers. So there are too many deep sky objects to name. You can't give a name to every one of them. So you make catalogs and give them numbers. And whenever we throw around numbers and names like M31, NGC, 224, whatever, we are referring to the object by means of its designation in some catalog. Okay, so there are many catalogs, maybe 50, 60, 100, I don't know how many. And they usually have a theme. Either it's all by the same observer, same researcher, same research program, or same type of object. Like there could be a cluster of catalog of galaxies, or it could come with special data that's relevant to researchers. Like there might be a catalog of all galaxies that have redshifts that have been measured, for example. So that kind of data. So catalogs generally fit into some theme. The other thing is one object may exist in multiple catalogs. The example I've taken here is the Andromeda Galaxy. Andromeda Galaxy is Messier 31, that's the first catalog. Then it's also NGC 224, same thing. It's also Andromeda Galaxy, different catalog. UGC 454, PGC 2557, all of these are names for Andromeda Galaxy in different catalogs. The first ever deep sky object catalog that was created by is the Messier catalog, which many of you are familiar with. It was created by French astronomer Charles Messier when he was looking for comets, and he wanted to catalog things that were not comets, right? So here are the famous catalogs. A Messier catalog was actually created by Charles Messier and Pierre Méchain, his colleague, or I don't know what the relationship between the two people is, but the last 10 Messier objects or so are actually discovered by Pierre Méchain. And then there's the New General Catalog, which is a first major cataloging effort, right? It's a systematic catalog of 7,840 objects. Most of the objects would have been discovered by either William Herschel or John Herschel II. But there are many other contributors to the NGC catalog, including James Dunlop. I think Lewis Swift, Barnard, all of these people were also NGC contributors. And the catalog itself was compiled by somebody else, J.L.E. Dreyer. And it's mostly full of visual discoveries. That's why this catalog is so popular amongst visual astronomers, because all of these were actually discovered visually. See, it's so much harder to discover an object visually as opposed to knowing that it's there and seeing it. So these are generally within the range of like 18-inch telescope. Then there are these things called the index catalogs, which are IC, supplements to the NGC, and that mostly comes from photographic discovery. So these objects tend to be very challenging. The other interesting catalog is called the Caldwell catalog. This is Patrick Moore. You might have heard of Patrick Moore. He was a famous astronomer who wrote many articles on amateur astronomy and many books and so on of that, so on and so forth. So he also created a catalog of 109 other bright objects for amateurs. So this is a catalog created for amateur astronomers. So once you run out of Messier objects, this is a good place to look for objects. So I think things like Sculptor Galaxy that Messier did not have because they were too far south, those are included in this catalog. Okay. Here are less famous catalogs that are common amongst amateur astronomers. This is a huge list. I'm not going to go over every one of them. You might have heard of UGC and PGC. These are catalogs of galaxies. PGC has way too many galaxies. There's Sharpless, which is a catalog of nebulae. There is George Abel's Planetary Nebulae catalog and Clusters of Galaxies catalog. So if you see numbers like Abel 70, whatever, that's what it means. It came from one of these catalogs. The interesting things here are that I want to mention is that there's this Mitchell Anonymous catalog. This was created by an amateur astronomer from Texas. His name is Larry Mitchell. It's only available in certain software, so it's only used by amateur astronomers. But I just wanted to say that there's an amateur astronomer who sat through, who looked through many photographic plates to find galaxies that didn't have other names, and he created his own catalog. So more about Larry Mitchell in the last part of the talk. Okay. Then there are obscure catalogs that are not very famous. Here are some examples. The Vorontsov-Velyaminov catalog of interacting galaxies is one such that was recently featured in the Sky and Telescope magazine by Steve Gottlieb. So there's catalogs that there are many catalogs that nobody has heard of, nobody has bothered observing objects in. So so the aim of this entire 3 slides is to introduce you to the famous catalogs and tell you that there are many more, and remove this notion of catalog fear. Just because it's in some obscure catalog doesn't mean that you cannot observe it. For example, I mean, if something is UGC, that doesn't automatically mean that it's faint, simply because even Andromeda Galaxy has a UGC designation, right? So that's something to be borne in mind. Okay, next big section is on the human eye. The eye is the sensor in visual observing, so understanding it is very important. We want to understand the human eye so that we can know how to use it correctly. Night vision is like a superpower. If you are not using it, you don't even know that it exists and how powerful it is. So that's why it's important to learn how to use it correctly. So I'm going to talk about physiology of the eye. By that I mean the structure of the eye, how it behaves in night vision, and so on and so forth. And then we will figure out how to use this in practice. We'll talk about how to use it in practice. The eye has 2 kinds of light sensitive cells, rod cells and cone cells. Cone cells are what we are all used to. Okay, cone cells are in 3 types. They are very roughly red, green, and blue. They work in bright light conditions. So chances are now your cone cells are doing most of the work. And they're responsible for color vision. This is why we can see colors. And the maximum density of these in the retina on the screen of the eye is along the optic axis. So if you look straight at something, chances are the light of that from that object is falling on cone cells, is activating those cone cells, and you are able to see in color. This is what happens in the daytime. In the nighttime, something completely, when you're, by nighttime, I don't mean like with lights indoors, like if you are out in a really dark place, a completely different set of cells is responsible for your vision. And that's the rod cells. These rod cells are very sensitive to light. They're extremely sensitive. And they work very well in dim light. Okay, so they don't have any notion of color. There is only one type of rod cell. The peak sensitivity of this is in the green part of the spectrum. Of course, it can't tell color, but it is most sensitive to green light. Okay, and the maximum density of these on the retina is actually away from the optic axis. So if you are directly looking at something, that light is not falling on the rod cells, it is falling on the cone cells. Okay. Now here is a cut section of, I got this from Wikipedia. Here's a cut section of the eye, retina, and it tells you, it shows you, see here, the cones are in the very center and the rods are actually on the sides. And on one side, there is this blind spot that we are familiar with because that's where the nerve connects to the eye, right? So, but the rods are on either side and the cones are in the center. Okay. So we'll talk about why that is relevant. Right now, I'm just talking about physiology. The eye has a really amazing intensity control. It can see 46.5 f-stops. This is what I saw on Wikipedia. an f-stop for most photographers know what that means, but otherwise it's a factor of 2 in brightness. So it can see this gigantic range of brightness. And how does it do that? Well, one thing that most of us know is that pupils dilate. So whenever you are in a bright region, the pupil, the black part in your eye, the opening in the eye is tiny. And when you get into a dark place, within a minute, it will expand and let in more light. So this is the intensity control. Just like you have in cameras, there is a intensity control. This happens within a minute. But the more interesting thing is that there is a pigment in the rods called rhodopsin. This pigment is chemically regenerated when you are in the dark. So when you are in daytime vision, this pigment is like it is on the left. So this is in daytime, this is what it looks like. Sorry, on the right. It's transparent. Okay, it is doing nothing. It's not absorbing any light. But if you go into the dark and allow things to settle for about 30 minutes, it slowly goes back into its original red color. Okay, so it becomes like this. So what this allows is the eye has essentially another intensity control, which is chemical, that is slow acting. But as this pigment goes from being transparent to red, it becomes very sensitive to light. And that is what is powering your night vision. So when you go to a dark place, initially you will not see anything for maybe 5-10 minutes, and then slowly you will start seeing more and more and more and more detail, and that's because of this chemical process. Okay. So here's a plot from this beautiful book called Visual Astronomy of the Deep Sky. It shows you how dark adaptation happens through this rhodopsin. Slowly, over a matter of 20 to 30 minutes, the rhodopsin is regenerated and the eye becomes much more and more and more sensitive. Okay, so, and it's slow. So dark adaptation, as we call it, which is the regeneration of rhodopsin, is very precious. We have to preserve it at all costs. Now, rhodopsin is a red pigment, which means it's virtually blind to red light. So the point is it reflects red light, right? So if something is red, then it reflects red light. And it absorbs all the other colors. So that means it's not going to be sensitive to red light because it is just reflecting it. It's not absorbing it. Instead, it is sensitive to, here, the green part of the spectrum. Okay, these numbers are in nanometers, if you know what that is. But all I want to say is that this part is green light. So we call this night vision mode of the eye as photopic vision. That's the technical term for the night vision of the eye. Okay, so all of this information, why is this important? Because now we'll talk about how to use it in practice. The first technique that comes out of all of this is averted vision, which many of you are familiar with. Because the rods are not along the optic axis of the eye, the best way to look at a deep sky object is you want the light falling on the rod. So if you just look straight at the deep sky object, the light will fall on the cones, nothing will happen. So if you want to see the object, you should actually look away from the object so that the light from the object falls on the rod cells. So a general rule of thumb is, so suppose this is the eyepiece and the object is here. So this is the object, DSO. Sorry, my drawing skills with the. Then if you're observing with your right eye, you should look here. If you're observing with your left eye, you should look here. Most people, just like they're right-handed and left-handed, they're right-eyed or left-eyed. You have a dominant eye that naturally you use to view. So if you're right-eyed, you look to the right of the object. If you're left-eyed, you look to the left of the object. Then what happens is the light falls on the rod cells. So then you are able to see the object in low light. The reason you don't look on the opposite side is because this blind spot is sitting there. So that's why you look away from your nose so that the light doesn't fall on the blind spot. It instead falls on the rod cells. Okay. So that's one lesson from eye physiology. The next lesson is that remember this curve that tells you where the rhodopsin is most sensitive. It's not sensitive to red light. So that's why we use red light to read our star charts, to find objects in the night, to move around, and to use our mobile phones if we have to. So that's why we follow red screening. So generally what I found is red screening apps, unless they are set up specially, they are usually insufficient. They still emit a lot of bright white light. So as if you're in darker skies, you want to do something better than just red screening app on your phone. And that's usually you want to use red gelatin sheet on touch screen, or this tape that you get called Ruby-Lit. One of my friends, Sanath, has actually opened up his Mac laptop and put a red gelatin sheet under the keyboard, so it actually turns red. He has a red backlight for a keyboard. But you can also buy keyboards with red backlight. I just use my red flashlight to see the keyboard. For computers, the best solution is to get this translucent red acrylic sheet. So you can have it cut in whatever size is correct for your computer, and then put it with rubber band around your computer. This thing is readily available in the US. I don't know how easy it is to get this in India, but I'm pretty sure if you go to like SJP Road, you might be able to find transparent red acrylic. So if you can find transparent red acrylic, it's just a matter of cutting it to the right dimension. Dimmable red flashlights. The word dimmable is very important, because a lot of the times, if you just buy a red flashlight, it will be too bright. And it can, even though the rods are not sensitive to red light, they have some response, and you can tell, because when you're looking at a star chart with a really bright light and then you look up at the sky, you can tell that it has affected your night vision a little bit. So that's why your red flashlight should be dimmable, and you should use as minimum brightness as possible that is needed to read the chart. Then use black insulation tape to cover all other lights. I have all the lights on my laptop covered all the time with black tape. And I just put the acrylic sheet on top of the laptop whenever I'm using it in the field. So this is some practical stuff that comes out of the fact that rhodopsin is not sensitive to red light. Okay. Here's another point. Every visual observer needs to get over the insecurity of darkness, because if you turn on a white flashlight because you're not sure what is in the bushes, you're lost. You have lost your night adaptation for a long time, and in fact, that makes you feel less secure because you can't see now anymore without the flashlight. So it comes with time. Initially, everyone is scared of the dark. Growing up in a city, you've never seen the dark. But it comes over time, and then you'll be fine. Okay, so that's like I said, even if you're using all red light, there is still some effect on the eyes. And I also feel like the sky itself is so bright, it can ruin your night adaptation. So you should always try to wear an eye patch on your on your observing eye whenever you're away from the telescope eyepiece. So even when I'm getting really serious and I'm looking for some faint dwarf galaxy, I usually have an eye patch on my observing eye. So I'm using the computer with my left eye because I'm right-eyed. So these are available at medical stores, so you can get an eye patch. During the day and when not observing, ultraviolet light has the ability to damage the eye lens and turn it milky. And we know that the very advanced stage of that is cataract, like when the lens is completely milky. You don't want that to happen. So to slow that process down, if you can wear ultraviolet protecting sunglasses, like most sunglasses, if you buy Fast Track or whatever, they protect ultraviolet. If you buy good ultraviolet protecting sunglasses, you can extend the life of your vision. Okay, a brief note on color vision. We just said that rods are insensitive to color. And so most night vision is black and white only. But if the object is bright enough, like ring nebula or some planetary nebulae, they can excite your cones. Some objects, not all of them. And everyone's color vision in low light is drastically different. So everyone sees color, different amounts, different shades. The easiest places to see color in the eyepiece are high surface brightness planetary nebulae. What that word means, I will explain what high surface brightness means. But basically, really bright planetary nebulae are where you normally see color. You see Ghost of Jupiter, a little blue. Saturn Nebula is a little blue. You can tell that color. It is possible to see color in Ring Nebula, Dumbbell Nebula, and Orion Nebula in big telescopes, especially if you use this flashlight technique, which I don't recommend. I cannot recommend, although it is effective. I learned this from Howard Banich, who writes for Sky and Telescope. The idea is you shine 1 to 2 seconds of bright white light, not very bright, like from a flashlight or something, on your non-observing eye to suppress the rods in your non-observing eye. So in my case, that would be my left eye because I'm right-eyed. And so when you're at a star party, of course, you have to be very careful not to disturb anyone else's night vision. And you should also protect your main observing guy's night vision. So use 1 to 2 seconds of white light and use that eye then at the eyepiece. You will actually see more colors. You might not see pink. You will probably see green and orange shades. But yeah, I've tried this on Ring Nebula. But it's risky. Some doctors said, I don't think it's a good idea. So try at your own risk. Basically, don't try. But it works. Okay. Now I'll talk about visibility of deep sky objects. I'm glad there have been questions about this. I did not expect that people would want to know about this stuff. Part 1 is basic. Part 2 is very theoretical. So if the theory goes over your head, it's fine. You're not missing out on much. Because in part 3, I will tell you that the theory has its own problems. So let's do this. So actually, before I get into that, any questions?
Akarsh, so I had some questions. So,
Yes.
what is the field of view of the eye? That's the first question. Second one, is there a resolution associated with the eye? And so, if you can compare to, let's say, a camera sensor, like how many megapixels would that be?
Oh, okay. The answer to both questions is I don't know. The field of view of the eye, I think, is the usable field of view is probably 80, 100 degrees. I really don't know what's the exact number, but you know that on the sides, it gets less and less effective, right? Especially in daytime vision, it gets less and less effective as you go towards further from the fovea, the optic axis. So in night vision, I don't know, really. The answer to the second question is that in daytime vision, we know that there's a visual acuity of about 1 arc minute or something like that. I don't know the number, but you can resolve some amount. It's definitely nowhere close to CCD camera. But in nighttime, it gets worse. Apparently, I learned somewhere, I've not read these articles in detail, but in glancing some articles on the web and as well as in various visual observing books, I think there is this idea that the eye in nighttime does something similar to what is called binning, right? Like it combines multiple rod cells to get one signal. So I think it's very complicated. There is one more graph in this book on visual astronomy that I keep mentioning, Roger Clark's book, that explains, I think, exactly this. It says that brighter objects appear more resolved to the night vision than fainter objects. So fainter objects, we are less sensitive to the detail. So the answer is complicated, and I don't know. That's the best I can do.
Thanks. One more question. So, what is the dynamic range of the eye?
Like I said, it's about 46 stops, right? But that's okay. Going, including the pupils adaptation and the rhodopsin adaptation, both.
Okay. All right. Thanks.
Right, rhodopsin itself is, the rhodopsin thing itself is extremely sensitive. I would not be surprised if it is like 20 stops or whatever.
Okay, but in terms of magnitude, how many magnitudes would that be?
That would be what -4 is the brightest Venus. I mean, if you ignore the moon, you can see -4, and you can see without. I mean, if you're dark adapted, I think you can see -4, and you can see 6 to 7, right? So that's about 10 to 11 magnitudes.
Okay, all right.
How fast is our eye?
How fast?
Yeah.
I don't know. There is a comment that I will make shortly. So the daytime persistence of vision is 1/10 of a second. So 10 frames per second or so. But we know we can, we want ideally movies to be at 24 to 30 frames per second. But at nighttime, I don't know. I suspect that it's slower. I suspect. So they say that nighttime the eye does integrate data just like a CCD sensor. But they say it's not very good at doing it. I haven't read the papers on this, so I'm not familiar with how fast it is. But I assume it also depends on what brightness we are talking about. Okay.
I think that should answer. I mean, even I was thinking the same. I mean, we can probably they meant what is the persistence of vision and the opposite calculation during the night. Yeah.
Yeah, I'm not familiar, but generally I think the vision is slower at night, and so it's like taking an exposure. That's why the experienced visual astronomers told me, and I think I believe it, that tracking makes a huge difference, because now your telescope is tracking, even for visual observing. Tracking makes a huge difference, because then your brain doesn't have to do that additional processing of chasing the object.
And there is also something which I had noticed, Akash. So whenever it is very faint or it is not at the center, or even if it is an averted, slightly moving the telescope or changing the field will definitely help.
Yeah, that's a very important technique, and I if I don't present it on day 2, then there's a problem. But yeah, that's a very important technique. You're creating some movements so that the receptors are not adapted. So yeah. Right.
Okay.
So Akash,
yeah.
So I think let's park for today, if you don't mind, because it's already 1 hour 45 minutes.
Yes.
Because we are at the right phase here. We completed the human eye, and then we are going to start the visibility of DSOs.
That's perfectly fine. If there are any more questions, I'm happy to answer. Otherwise, we can pick it up from here tomorrow. Or like what I mean is next week.
When you, it can go to f42 as a aperture value of an eye pupil. What is the lowest number to an eye?
So that it's not the same as f42. When I say stops, it's using that as a measure of. Sorry. When we say 46 stops, we don't mean that aperture control is 46 stops. That's not true. The pupil's range is from about 7 millimeters to 2 millimeters. And that will not cover how many stops is that? That's 7 square minus 2 square roughly, right? Is that divided by 2 square, I think. So I'm not sure exactly how many stops that translates to, but 7 square divided by 2 square. That's the number we are looking for. 4. So about 12 stops in just the pupil. The real intensity control is in the chemical reaction. So when we say 46 stops, we don't mean that the eye aperture is changing 46 stops. It's really combining the chemicals effect. That's the entire range of exposure values, if you like, from photography that it can handle.
So like in photography, we have, I recently read somewhere like we can go up to 0.98 f value of a lens, so prime lens,
Yeah,
right?
yeah.
So from that angle, I'm not talking about your chemical composition of an eye, which happens in the night time. What is that value? 2.8 somebody said, but I don't think like 2.8 will be the correct
So I
number.
don't know the answer. We'll have to divide what is it, the 7 millimeter diameter of the open pupil with the focal length. I don't know what the focal length of the eye is on the top. I'm not familiar with it, but it's a calculation that can be done, right? So
Okay, thanks.
I had one question.
yes.
Hello. Yeah. So how far can we see using an 8-inch telescope, roughly speaking? I mean, the farther we see, the more redshift it will become, and until a point, it will be too much redshift we can't see anything. Is that the limit for an 8-inch also, or is there a limit at all?
I don't think redshift is the limit. That's a good point. Yes, definitely. The galaxies and quasars that are further out are harder to see because of redshift, and the more redshifted it gets, the less your eye will respond to it because night vision is not sensitive to red. That is a factor, but I think the bigger factor is just that things become fainter and fainter, right? Your average quasar, whatever that might mean, you might not get like something that's really far away. You might not be able to see simply because it's faint. I think the number that I can quote off the top of my head is the furthest object that most people have comfortably seen in an 8-inch would be the quasar 3C273, and if I remember right, that is 3.7, no, 3 or something like that billion light years away. I should look it up. But 3C273 is visible in an 8-inch. I think it's 13th magnitude or something. So generally, it's the biggest, it's the furthest that people have seen with an 8-inch. But I won't be surprised if there are other quasars that people have managed to see.
Thanks, Akash. That helps.
Sure. But generally, I want to mention one more thing. This notion of what is the furthest that you can see in an 8-inch is or in any telescope is a very misguiding notion, right? Because quasars are extremely bright. You can see a quasar at 3 billion light years without trouble, but you won't be able to see galaxies at 3 billion light years, right? So it depends on the brightness of the object. Then again, it depends on what galaxy we are looking at. I remember we had a talk at Texas Star Party by Jimmy Lowry that said, what are the NGC objects that are a billion or further light years away? And there was a list of maybe 10 or 15 NGC objects, some of them spiral galaxies, individual spiral galaxies, and those are extremely challenging. Like, even though you might need like a 24-inch, 36-inch, that kind of telescope to manage to see those. But at the same time, even in an 18-inch, modest 18-inch, if I may say so, in this amongst these people, you can see this Corona Borealis cluster, where the bright galaxies are about 900 billion light years away. So that notion is very rough. Like I said, you can see a 3 billion year light year quasar in an 8-inch telescope. So I think it's 3 billion. I'm not sure. I have to check 3C273. Sure, yeah. What is the...
Okay, guys, any more questions? Yeah, you can unmute yourself and ask.
Sorry? Oh, unmute. Okay, cool. Got it.
Okay, well, I don't see any new questions in the chat as well.
Okay.
Yeah.
So when do we have the next session, Akarsh?
I'm okay to do it next weekend, just like this, is this a good time that works for most people? I would prefer my evenings and nights.
I think so. There were more than 60 people who were attending, so I think people are okay with this time.
Okay. Sure. Then we will keep this time next weekend.
All right. Awesome.
Perfect.
Thanks, Akarsh, for the session.
Okay. Thank you, everyone, for the questions and all the participation. I really enjoyed, and we'll reconvene.
Thank you very much.
Sure.
Thank you. Thank you, Akarsh.
Thank you, guys.
See you.
Yeah. Bye.
Thank you.
Bye.
Bye.
Bye. Bye.